Overfitting the data is a key concept in machine learning. It is absolutely crucial that you understand it. So let's look at some slides to try to get underneath this critical concept. Okay, so consider the following random points. These are actually randomly generated. Now, the idea here, we're just looking in 2 dimensions, is what's a potential mathematical model that we could come up with to sort of map these points, right? Like, what kind of a function can we create to capture the relationship of this data? How does our input X influence our output Y? Okay, well, you can look at polynomials and you can ask the question, what degree of polynomial will fit the data best? Okay, well, here is a first degree polynomial. This is a straight line, and this is the least squares regression line, and it has what is called high bias, okay? This is clearly not overfitting the data, okay? This is the opposite, right? This is underfitting the data. So what does underfitting mean here? Well, the regression line fails to pick up on nuances of the data. I mean, that does not capture the relationship. It's almost horizontal. It just doesn't do a good enough job. Okay? I think that's pretty clear. Now, compare that to the following. Okay? This is an 8th degree polynomial, and it has what's called high variance. So this perfectly captures the data, right? This is a perfect model. And so, your initial kind of thought might be, well, that's great. Now, if we were simply curve fitting, we've done it. We have, found a curve that fits this. No matter how many points you have, you can fit those, points with the right degree of polynomial. So what are the issues here? Well, this is what we would call overfitting the data. Okay, and this is our key concept. So why is this not good? Well, the polynomial is going to generalize poorly to new data. Imagine that you have a different x, right? That's different than the ones on here. And what's happening is it's going to be forced to fit to this polynomial. This polynomial is very particular based on the previous x's. Okay, so let's take a look at some examples. So if x was 1.5, so we're about down here, well, y would be 11. Now, that fits the polynomial, but it doesn't seem to really fit the data, right? The data, you wouldn't think that given these points, well, if you're between these two, it's going to go way up here. That's more like this unique, it works for this unique curve, but is that really the relationship? What about when x is 8.5, you're over here? Well, now you're entering negative terrain due to the polynomial, which given this data, I would not assume that there are negative values at all. So I don't think that that's good. But even more problematic, look at the ends. So when x is something like 10, I don't know what it is exactly. It's something like 250. You're way, way up there. It's way out of range. And this is just not good. This is what you call clearly overfitting the data. With the key here is that when you build machine learning models, it's not just about the data that you have in front of you. Okay, you can sort of force it sometimes, not all the time, to perfectly fit that data. But the issue is you actually want it to generalize well to new data. And this polynomial is not going to do that. Okay, so let's take a look at some other examples. So here's an interesting example. What's going on here? So if we look at these two polynomials, this is kind of like what we saw before. We have a perfect polynomial, which is the blue curve that fits the green dots exactly. But we also have a green curve that is the least squared regression line of these green dots. Now, if I asked you, which sort of polynomial do you think would be best for capturing the real relationship between these data points? You can make arguments for either one, I suppose, but I think in the world of machine learning, most of us would probably choose green because we think it's going to generalize well to new data, right? If we have an X value of, say, 50, the trend is that these keep going up. We're going to assume it's going to be up where the green is, not like way down with some crazy negative value where the blue is. Now, in this particular graph, they're showing these red dots, and the idea is that I think these are points that are sort of known, and it's like, well, which one would they go to? So these are pretty close to both, like the red ones. But you can see overall, if you look at them in sum, they are in fact closer to the green. Okay, so we would say that the green here, I would say like this, it's rare that data is linear. This data looks pretty linear. I think a linear model would be strong here to generalize well to new data. Those are the predictions. That's the goal. It's not curve fitting, okay? Machine learning is not about curve fitting. The blue curve does that, but it's just not good enough, okay? Here's another fun one. So what do we have here? Here we have, again, two different curves. And the idea here is you're splitting the data into two groups. Sort of the green curve kind of precisely divides the data into the blue points to the right and the red points to the left. But we also have this general smooth curve, which sort of does a nice job, even though it gets some of the points presumably wrong. So in this particular case, you might wonder, well, okay, but if the green curve is getting it right, like, why is that not better? Well, let me give you a couple of ideas here. First of all, what if some of these are mistakes? Like, what if this one should actually be blue? Okay, that would completely change the curve. And so one issue of overfitting your data is that you may sort of run into, errors, and you may sort of be working with those errors. The other thing, if it's not an error, it could be something else. So it could simply be an outlier. Okay, this red, it could be an outlier. This one could even be an outlier, right? Well, what does that mean? What if you have some points underneath here? Well, they may actually be blue, right? Because this outlier sort of stands alone. And you don't want to sort of, again, overfitting is the key word, overfit the data to deal with sort of like these unusual points, these outliers. And one of the reasons why also is because these models are not going to be or sort of 100% accurate. You'll kind of build up to that understanding. It's sort of like, if you could just easily get 100% accuracy, machine learning isn't even always necessary. The idea here is machine learning is necessary because there is not 100% accuracy. We need to sort of make predictions to the highest probability that we can. Okay, so you don't want to overfit here on your training set. I would say this one's a little closer, but I would go with the black curve because it's sort of smoother and it could generalize better. Imagine you drop in 1,000 new points here. Okay, so what are some solutions to overfitting the data, which we're seeing as an issue within machine learning? Well, the first one is to split the data into a training and test set. Okay, this is essential. You must split your data into training and test sets. If without doing this, the models are too good these days, they will likely overfit the training set. So the idea is to enforce that it sort of generalizes well to new data, you're going to score it on data it's never seen before, and that you could call for now your test set. Okay, you can also call it your validation set, but more on that later. Another solution is to use models with built-in regularization. You could think of regularization as sort of a keyword in machine learning, which means preventing overfitting. So certain models have different built-in parameters that deal with this up front. Another solution, which we'll look at later, is you can train and test on multiple folds of the data, not just one, which is called cross-validation. And finally, you can adjust the hyperparameters. These are sort of the, we've looked at parameters that you can change. They're called hyperparameters, in effect, to be distinguished from parameters, which are sort of the weights that the machine learning model is always going to adjust. You don't control those. The model adjusts those to your data, but you do get to control some of the hyperparameters like the max depth of a tree. By adjusting these, depending on the model, they're different for all the models, You can also reduce overfitting. And we're going to look at in this lesson how to split data into training and test set and how to adjust hyperparameters to reduce overfitting, though we will look at the other options later.